So we can also prove that these harmonic series are divergent or have an infinite sum by looking at the area of the curve of y equals 1 over x. Okay, because y over 1 over x behaves like our harmonic series. Although the areas don't quite match, the behavior is the same. Okay, so this is an improper integral. Okay, so we've integrated these before, and in fact we've actually done this exact same one before. But let's do this again, and we can see that the area under the curve of this integral, although it's not exactly the same as the area under the curve under the rectangles here, okay, of this harmonic series, you can see that there's a little bit of a mismatch, but regardless, they will behave the same. And that's a truth in that although the sums are not going to be exactly the same, the curve behaves like the sequence, okay? So integrating this, we're going to start off here, and then we're going to integrate to infinity. So this is an improper integral. To set this up, we need the limit as x goes to, a goes to infinity. And it's the integral from 1 to a of 1 over x dx. Okay, so then we write this as a limit. A goes to infinity. We anti-differentiate that to negative 1 over, so that's going to be log x. Okay, and then we're going to integrate from 1 to a. We can evaluate this integral now, so the area is going to be equal to log of infinity when we plug in the a minus log 1. Okay, so log infinity is in fact infinity, minus log 1 is 0. So the area under that curve is infinite. Okay, so although, like I said, the area under the curve and the area of the sequence there's a little bit of mismatch, but they behave exactly as they behave similarly. And so if one converges, the other converges. If one diverges, the other one diverges. So there it is. That is the area under that curve is infinite. Okay, so the basal series is slightly different. It is a p series, just like the harmonic series is a p series as well. In this case, our harmonic series, the harmonic series p is equal to 1, but in this case, the basal series, the p is equal to 2. Okay, so it looks like this. So we end up with this series of 1 plus 1/2 squared, 1/3 squared, 1/4 squared. And this sum adds up to, and we're not going to justify this, but it happens to add up to a finite sum of pi squared over 6. Now, this is interesting because very few infinite sums, it's very hard to actually calculate a number for them. Unlike integrals, we can calculate numbers for these discrete sums. They're very, very hard to calculate actual values for. We have a sense of where they're going towards, right? If they converge to a number, we have a sense of what that number is. But these numbers are very, very hard to calculate because we have to do an infinite number of calculations. Well, that's impossible. So we have to do some other proof. This one's been proven that this sum is equal to pi squared over 6, okay, which is approximately, 1.5 or so, right? A little bit more than 1.5. Okay, so the sum of this series happens to be pi squared over 6. And this is only slightly different than the harmonic series, but it's different enough such that it converges. Okay, and this is a very, very well-known series called the basal series. So this p series, all p series that have p's greater than 1, okay, so the denominator is bigger, they will converge to sums. Most of them we don't know what the sum is, but this basal series, somebody spent a long time to figure out that it was pi squared over 6. But for our purposes, we don't really care what the actual sum is. We just need to know whether they converge or diverge. We're not in the business of calculating these sums. That is way too hard. Okay? But we are going to look at whether these converge or diverge. and all p values greater than 1, so okay, so anything where the power is bigger than the harmonic series converges. Anything less than the harmonic series is going to diverge, okay, because it does not go down to 0 quick enough. So the harmonic series would look like this. Okay, there's our boundary series. And then we have p series that are less than 1. They will have curves like this. Okay, and with p series greater than 1, okay, we'll just say that the black one, these ones are p series greater than 1. They will be below that green line. And that green line represents our harmonic series, which is our boundary. Okay, this represents a boundary. This is a boundary between diverging and converging. So this leads to a paradox in that there's this thing called the harmonic series paradox, in that if we actually draw this out, and you can watch the video as well, but if we actually draw this out like this, okay, so we have 1/2, okay, we'll just say 1, okay, this length will be 1/2 in here, okay, so we're gonna actually, I'll show this as 1 plus 1/2 plus 1/3, okay, make that a little bit shorter, plus 1/4 plus dot 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 dot. Well, that is a harmonic series, and we know that equals infinity. So if I were to draw this line, okay, a line along that axis, so this purple line here, that purple line, if I were to draw this out, it's going to be infinite. Okay, so it's going to, I would need an infinite amount of ink to draw that purple line. Now, the basal series is this. Well, it's going to be 1 squared. Okay, well, that's 1 squared. That's the area of this square. And then the next one will be 1/2 squared. And the next one will be 1/3 squared. Okay, the next one will be 1/4 squared. And we know that this series is the basal series, and that has a finite sum. In fact, this area is going to be about 1.5 something. Okay, so I need a finite amount of paint to fill this area. Whereas if I were to draw this line, and this area goes infinitely, okay, so I would need a finite amount of paint to paint this infinite sequence here of the basal series. But I would, in this case here, and there's a match to this harmonic series goes just as far, but if I were to draw this harmonic series line, I would need an infinite amount of ink to draw that. I need a finite amount of paint to paint this area, but I need an infinite amount of ink to draw this line. And there's a paradox. That's a paradox that we run into. This is called the harmonic series paradox, and that the video will explain a little bit better.